Okay, let's get back into fun proving things. Okay, guys. Okay, so any questions on the reasoning that we have done so far? So this reasoning holds for any regular language at all. So it's not just unique to this language with the same number of zeros and ones, but rather any DFA has this property that if you feed it a string long enough, some state will repeat. So let's actually prove something very important, something that strikes fear into all computer scientist students the world over. You ready for it? The pumping lemma. Everyone groans now for regular languages. Okay? So, in fact, we already proved this lemma, so we don't have to do a proof anymore. But we're just going to state it more formally so that we can apply it later. So, what we have done so far is we looked at a regular language. We saw this long string that's accepted, but we found many more strings that we can get just by doing the loopy part many times. We found many other strings that are also accepted. That's what the pumping lemma says. It says if you have a regular language and you have a string that's long enough, whatever that means, then you can find many other strings that are also in the language, meaning the DFA accepts them. So the statement is let L be a regular language. And notice, I'm not going to say DFA at all in this statement of the lemma. I'm just going to deal with languages and strings. That's it. So L is a regular language. Great. Then there exists a, quote, pumping constant, which I'm going to call P for L. So I want you to think of this constant P as the number of states in the DFA we looked at, the N that we had before. I probably should have called it P before, but I thought of N at that time. So but notice, L is a regular language. There is a constant P for L, meaning there's a DFA for the language L. That means it has some number of states. P is the number of states for that DFA. Okay, so there exists a constant P for L, such that, well, here's the thing. What did we look at? We considered a string that was long enough, but what else did we need to have to be true of that string with respect to the language? Was that string that we considered the long string, was it in the language? Yeah, it was in the language. What if it wasn't in the language? Could we infer anything about other strings also in the language? No, because if we do the loopy part, we're still going to end at a non-accept state. So we need to consider only the strings that are in the language, because then we can infer other strings, and long enough. Why did we need strings that are long enough? What if the string wasn't long enough? What if the string that I picked here, where this had n states, I picked a string of length n minus 1. Could it be possible that we don't repeat a state anywhere? Yeah. So in fact, we need the length of the string to be big enough, such that for all strings W in the language and having length at least this number P. So I'm not going to consider any string that fails one of these two stipulations. If it's not in the language, I do not care. If it has length shorter than P, I do not care. If you fit both of these, then proceed after this. Okay? Okay, great. Well, let's see. Let's go back up. So notice that the W string that I wrote here, it had an X part, a Y part, and a Z part, right? Is this the only way to write it as an X and a Y and a Z? Could there be another loopy part somewhere else? And I could write the X part as something else, the Y part is potentially something else, Z part is something else? Could there be another way to write it? Yeah. So, but do we care that there are many ways to write this? But do we only need one of them to work? So if I find one of these ways to break it up into 3 pieces, is that enough? Yeah, because then we can do this analysis and then do the loopy part as many times as we want. So that there exists, so that means there's at least one way to do this, a decomposition of that string W into XYZ. So we're considering these okay strings that are in the language and long enough, then there's a way to break it up into 3 pieces, like in the diagram we did before. Well, but those 3 properties must also hold, such that then the 3 stipulations occur. That x, y to the I, z is in L for all I, at least 0. Y is not the empty string. I'll write that better. And the length of x, y is at most this number p, which is the corresponding number of states in the DFA. Bam, done. But think about what we're doing here. We're saying we have a regular language, and we consider strings that are long enough and are accepted by the supposed DFA. And then there's some way to break it up into 3 pieces such that we can go around the middle piece as many times as we want and get other strings. That's essentially what this is saying. Okay, any questions about that? Here's the thing. Does this say anything about a language not being regular? So let's see. If we have a regular language, then these properties must hold. What if the properties don't hold for a language? Oh, it's not regular. Wait a second. So that language that we looked at earlier that appeared hard to do, that had the same number of zeros and ones in the string, if we prove that these properties can't hold, what can we conclude about it? It's not regular. So it's the contrapositive of this. So this says, if it's regular, then these properties hold. What if we did it the other way and negated both parts? We said, if it doesn't have these properties, then it's not regular. It's the contrapositive. Is the contrapositive equivalent? Where should you look this up? Chapter 0. Okay? Contrapositive is equivalent to the original statement truthfully. So, cool. Let's try that. So let's try to prove, and we will prove it, the language L, which has the same number of zeros and ones. This language is not regular. Dun, dun, dun. You guys are a tough crowd. My goodness. Okay.
It's 7:30
It-
at night.
Well, it's not even 7:30. It's 8:50.
8:50 at night.
Cool. All right. So it turns out that this language is not regular, as I have hinted before. So let's see. How would we even do this in a contrapositive-y kind of way? Or in a contradiction type way? So let's see. We don't know if L is regular, right? Because this is trying to prove it isn't. Well, we haven't done the proof, so we don't really know that it's not regular. Could it be regular if we just ignored this theorem statement? It could be possibly regular. We don't know. But what if we suppose that it was regular? What has to happen according to this lemma? The three conditions must hold because we suppose that it's regular. What if we reach a contradiction? Then it can't be, because then the properties won't hold. See how we're going to do this? Okay, so let's actually prove this. So let's suppose that L is regular. And in this proof, we're not going to say DFA at all. Well, we're not going to say anything about, yeah.
So we're trying to prove like that any one of these is not like it doesn't hold any of these three. So
Yeah, so
for all of them, are we trying to prove that once?
I'm gonna address that. Yeah, we'll get to that. So, but that's our plan of attack. If some of these properties don't hold, then we're all set, because then that'll contradict the supposition that it's regular. Fine, great. So what do we know about L then? If it is regular, we're supposing it is regular. What exists for it? Well, DFA, but I'm not going to say those three letters again.
There exists like pumping constant.
Yeah, there's this pumping constant P for L, right? That's what the lemma says. Okay, so whenever you are stuck with a proof or something, try to apply the definition or the statement of some theorem directly. So if it says like there exists something, write down that there exists that thing, because that's what the theorem statement says, or the lemma statement, I guess. Then there exists a pumping constant P for L. Because that's what the lemma says. Excellent. Let's go back up. So what does it say after the pumping constant part? There exists a pumping constant P for L.
Such that for all the W.
Oh, okay. So it says for every string in the language that's long enough, properties hold. Okay? So it says every string works that's long enough and in the language. What if I showed you one of them that doesn't work? Would that be enough to contradict this, the for all statement?
Yes.
Cool. So let's pick a string that we think will not work, okay? That we'll be able to show a contradiction. So I'm going to pick it for you first, and then after this, I'm going to let you guys pick. So we're going to pick the string. W equals P characters of zeros followed by P more characters of ones. So a string of P zeros at the front, P ones at the back. Okay? What two properties must hold of this string?
Same number of zeros and ones.
Same number of zeros and ones, which means it's in the language. Is that true of this string? Yeah, it has the same number of zeros and ones because there are P zeros at the front, P ones at the back. I don't care that the zeros are at the front, but the same number of them appears. What else has to be true of this string? The length has to be at least p. Okay, is the length of this string at least p characters? Certainly, yeah, it's 2p. So this is actually one of the hardest parts of the entire proofs when students do Pumping Lemma type proofs, is that they pick a string either that's not long enough or is not in the language, or both. Okay? So always pick a string that's long enough and is in the language, because we want to get a contradiction. This says it works for all strings. We're going to show that that one example does not work. So therefore, the for all statement's not true. Okay? Okay, great. So that's fine. So what does it say after the stipulation on L, that is, the stipulation on W, that is in L and has length at least P? What appears after that? Yeah, there exists a decomposition. Okay? So the lemma says, if the language is regular, there is a way to write it into 3 pieces. What are we trying to do? We're trying to do a contradiction style proof. So is showing that one decomposition that doesn't work, is that enough for us to show that one decomposition doesn't work? Or do we need to show every decomposition doesn't work? Well, what if I show you all of them don't work except one of them? Could that one that's left still work? Yeah. So I want to show that every decomposition doesn't work, because then there's no chance that this could be applied, that some decomposition can sneak through and show that our proof is wrong. So we need to look at every decomposition of this string into 3 pieces, okay, such that the properties hold. Okay, well, let's see. There are a lot of decompositions. The X part could be empty. We know the Y part can't be empty, but the X part could have some zeros, the Y part could have some zeros and ones, and then the Z is the rest of the string. Oh, or X is all the zeros, Y is a single one, Z is all the rest of the ones. But there are many other ones that we could have picked. Right? There are many other decompositions we need to consider. Does that sound like a pain in the butt? Yeah. Is there one of the 3 conditions that can really help us? Hint is number 3. Number 3, why does that help us? If the length of X and Y together is less than or equal to P characters. For this string, 0 to the P, 1 to the P, where do the X and Y parts have to be if their length together can't be more than P characters? Oh yeah, it can only be in the zeros. So the X and the Y part cannot ever have any 1s. You see why we picked P characters for each of the 2 pieces. Because by doing that, we can guarantee that the X and the Y part are both in the zeros, contained in the zeros. And because of that, it doesn't really matter how many zeros they have or where they are in the string. All that matters is that they're in the zeros, which helps us. Okay, great. So therefore, we know that the X part has some number of zeros. We don't know necessarily how many, but it has some number. And Y also has some number of zeros. Could the Z part also have some zeros? Yeah, because if the XY part is shorter than P characters, then the Z part has to take over the rest of the string. So it must take all the other zeros with it. Well, let's see. Then we know all decompositions. So I'm intentionally going into more detail for the first time then the next times we're going to make it more easy to write all of this out. So you don't have to write this every single time, but it's just a good habit to get into. At least get some of it. So then we don't know all decompositions look like this. So we know the x part is something, the y part is something, and the z part something. So we know for sure that the x part only has zeros and nothing else at all. But we don't know necessarily how many. So we're just making it look like a particular decomposition. So I'm going to write this as 0 to the alpha, where alpha is at least 0. So all I'm saying is that the x part has some number of zeros, at least 0 of them. Some number of zeros. And does the number of zeros in y depend on the number of zeros in x at all?
Yeah.
Well, we'll deal with that, yeah.
Don't we have to limit alpha to be less?
Yeah. We won't actually worry about that. But yeah, we do have to limit alpha, yes. So yeah, you all raised the right point that we will limit alpha technically, but I'm just worried about, does the number of y's depend on the number of zeros in x? Could they have independently many zeros? In fact, they can. So I got a no, maybe, and I said yes. So you're technically all right. So, but let's just handle this in a generic way. I'm going to say that y has beta zeros, where, what do we know about beta, the number of zeros in the y part? What has to be true? Can it have 0 zeros? No, y is not the empty string. That's what's going to get us the contradiction eventually. So we know that beta must be at least 1 because there's at least 1 character in y. And we know that because of this, alpha plus beta is at most the number of characters in that first part p. We're not actually going to use this because it's just not going to be useful to us. But you're right, we should consider that to limit what they could be. Well, let's see. How many zeros are left for the z part? Right, yeah. So we started off with p zeros. The x part took alpha of them away. The y part took beta of them away. So I'm left with p minus alpha minus beta zeros. Are all the ones still left? Yeah, because the x and y part, again, never touched the ones. Okay, so there are p minus alpha minus beta zeros for the z part, and all of the ones are still left for z. Excellent. We're almost there. It's one more line, I promise. And I'm out of water. Great. All right. Let's go back up. It says, well, okay, so we found our candidate string that's hopefully going to get us a contradiction. We looked at every decomposition according to these rules. But what is the contradiction we want to get? Look at the first statement here. It says that x, y to the I, z is in L for all I at least 0. For every single value of I is always in the language. What do we need to get a contradiction? What if I showed you one value of I that's not in the language? Does that contradict the for all statement that it is in the language? Yeah. So if we pick a single value of I that gets us out of the language, is that enough? Yeah, that's enough. Cool. So let's see. Do we know necessarily which I to pick? Well, this is your first time, so probably not. So it'll turn out any value other than 1 will work. Why can't I pick 1?
We already used it.
Yeah, because that's the original string. What do we know about the original string? Is it in the language? Yeah, we forced it to be. So it'll turn out any value of I other than 1 will work, but pick a value of I that's not 1.
2.
2. Let's pick 2. So it's x, y, this is usually called square z. But this is just x, y twice z. Well, let's just simply just write it out. Well, x has alpha zeros in it. So, and there's 1 copy of x. So I write alpha zeros out. There are 2 copies of y, which means I'm going to write 0 to the beta twice. And then the z part, which is the p minus alpha thing. We're just looking at a string. That's all we're doing. Ooh, we got a lot of zeros on the front. How many zeros do we have? 4. Hopefully more than 4. If you want to troll your teacher sometime, if they ask like a high-level question like that, that depends on a numerical answer, just say like 3 or 4 or something. Yeah. All right. But really, how many zeros do we have? Well, let's see. We have p in them. We have an alpha at the front and a minus alpha at the end. So I think those alphas cancel each other. We have a beta at the front and a minus beta at the end. So those betas cancel. What is left after the dust settles? P plus beta. Yeah. So p plus beta. Perfect. And all of the 1s are still there. Excellent. What do we want to know about this string? Same number of zeros and 1s. What has to be true if this string has the same number of zeros and 1s? Yeah, so this implies that beta must be equal to 0. Because if it's not, then it has a different number of zeros and 1s, which means it's not an L. So the only way it could be an L in the language is if beta is 0. But is beta equal to 0? Ooh, that's a contradiction. Oh, so we found a value of I that allowed us to get out of the language. What does that tell us about the language itself? It can't be regular, because if it was, then we would always stay in the language for every value of I, but we found one that doesn't work. So therefore, L is not regular. One of the interesting questions I actually looked at last year and actually published is, this language is not regular, like the same number of zeros and 1s. But if you look at the one that I told you earlier, the same number of 0 1s as 1 zeros, that is regular. When is it that something equals something in the same number of both? When is that regular? It's actually an interesting question, but it's way more complicated than what we're going to cover. But any questions on this proof? So let's recap. We wanted to show that this language is not regular because we had the intuition that it wasn't. We suppose that it is regular, which means that we could apply the pumping lemma. There's a constant p for L. We picked a candidate string because it said that all strings are going to work. If I find one string that doesn't work, then we're all set. Then it showed that there is some decomposition that works in the lemma statement. There's some decomposition that works because other ones could work. If I show you all decompositions could not work, therefore there can't exist a decomposition that works. And then we looked at, well, if we looked at some decomposition, it said that if we looked at x, y to the I, z, that'll always stay in the language for every value of I that we pick. But if we find one value of I that lands us out of the language, therefore that'll contradict the for all statement that it'll always stay in the language. And that's exactly what we did. So therefore we got a contradiction. Therefore our supposition was wrong that the language was regular, so therefore it isn't. Okay? Any questions about the proof? Yeah.
How important would you consider like having an in-depth like understanding of the proof?
It's not an understanding of this proof, it's an understanding of the techniques used in the proof. So the techniques of picking a string, a candidate string that'll work, because I'm going to actually show you examples in the next example of strings that will not work. Yeah, so that sort of thing. So it's just getting an intuition of why we're doing things this way, and picking strings where the decomposition technique part is easy. Because if we look at all decompositions in total, that's a lot of work to do. But if we can boil it down to a simple one-case analysis like this, then that's a lot easier. So we can just say, oh, the x part has just zeros in it. Some number zeros, but it's just zeros, and then y is just zeros. What if I pick the string, and I'm gonna put this in red. What if I pick the string 0 to the p over 2, 1 to the p over 2, and I'm gonna assume that p is even, for example, so that there's no fractional part. What makes this string a lot harder to use? This string will work. There is a way to do it correctly, but it's a lot harder. Why is it harder? What do the decompositions look like? Could the y part go into the ones? Yeah. So we need to be able to handle those cases differently too. Okay? So being able to pick a string such that you contain the x and y part you quarantine it to just one part, that's a lot easier than having it be anywhere in the string. So, yeah. Any other questions? Yeah.
I'm not sure that I understand how we know whether the y is part of the zeros and ones.
Because of the third stipulation right here. Because the length of x, y together is at most p characters. We ensured that the first p characters are all zeros. The xy part might take up all the zeros, but it can't take up any more because the xy part is at most p characters in total. So we ensured that by having the first p characters be zeros. That's one of the issues with the string in red, because not the first p characters are all zeros. The second half of them are ones. So that's one of the reasons why we picked this string, because it's a lot easier to work with. But we know this because of the third stipulation here. Other questions? Okay. Let's do another example, because more examples are good. Anyone have family who you think just repeats themselves a lot? I do that. I do have family like that. Let's consider the language of repeating yourself. Wasn't that a good segue? All right. So let's look at L2. Let's look at all the strings WW. So the same string twice, where the string is just a binary string. So you may think, oh, isn't this concatenation? Isn't this concatenation? Think about it. What is concatenation? You pick a string out of the language, and then you pick a string out of the language again. Do those have to be the same string? No. This is picking the same string both times. So concatenation is not this. Concatenation is picking any arbitrary two strings. They could be the same, but they can be different. Whereas here they have to be the same. So that's actually a major difference here. What did we show about regular languages with concatenation? They're closed under concatenation. This language will not be regular. So try to not fall into that trap that this looks like concatenation, no, therefore it's closed under it. So this language is regular. That's not true. So let's prove this is not regular. So I'm going to get you started on the proof, and then I'll show you strings that won't work to get you an idea of how to approach this type of thing in the future. So suppose, I'm going to shorthand this a little bit. Suppose L2 regular, then exists a pumping constant P for L, just like before. So we're going to suppose is regular, just like before. Then there's a constant P for L, whatever that is. And then what do we do next? Well, what did we do before? Yeah, we picked a string because we wanted to show one string that doesn't work. So I'm going to show you strings that do not work, okay? So you may think, okay, and I'm going to put them in red so that you know. Let's choose W equal 0 to the P, 0 to the P. Well, let's make our checks. What checks do we have to make? What are how many checks do we need to make? Two. And what are those checks? It's in the language. Is it in the language? Yeah, so that's good. What's the other condition? Is the length of this string at least P? Cool, it passed both checks, so we should pick this string. What's wrong with this? Here's a decomposition of this string that no matter how you pump it, so putting more y's in the string, increasing the value of that I exponent, that's called pumping the string. Here's a decomposition that allows you to pump the string as much as you want and stay in the language. Pick X to be the empty string, Y to be 0, 0, and Z is the rest. If I put in as many Y's as I want, am I going to ever leave the language? No, because it'll always have an even number of zeros. Okay? If I took away Y from the string, I just removed it, do I still have an even number of zeros? Yeah. So because we have an even number of zeros, the first half of the string is equal to the second half of the string. So therefore, it's of the form WW. So therefore, it's in the language. So there is something wrong here. Okay? Okay, great. So we better not choose the string. Should I pick 1 to the P, 1 to the P? Here's a string that I see all the time from students, and I hate seeing it on tests when they write this for a lot of points. Pick the string, so we don't want a string of all zeros for obvious reasons. So let's pick 0, 1, 0, 1. So it's the same string twice, 0, 1 with a 0, 1 after it. So it is the same string. Oh, let's pick this string. What's wrong with it?
You already agree.
Well, is it in the language? Yeah, it's in the language because it's the same part twice, so we should move forward.
It could be more than four.
Ah, does it have more than P characters? No. So we don't know the exact value of P here. We just assume that constant exists. I don't know if P is less than 2. I do not know that. But I know it exists. And I do not know whether this string will work because I don't know if it's long enough. So this string will not work or is not sufficient to prove. What is a better string to prove based on these two examples, do you think? 0, 1, where's the P? So the choice that you made was this one, 0, 1. Is it contained around 0, 1? Okay. So now you just made yourself, your life way harder. Ha ha ha, evil laugh. So why is it difficult? The reason it's difficult is, look at the first half of the string. It looks like this, right? So that's the first half of the string. Well, consider all decompositions. Well, what could happen is that the X part, it has to start at the beginning, but it could end up not on the barrier between a 1 and a 0 coming after. Then this is like the X part, this is the Y part, and then etc. So it's a lot harder this way. The reason we did the string we did before was the X and Y parts are uniform in what the characters are. They are only zeros, so we only have one case to deal with. You can go with this, it will work, and you will get a contradiction, but it's a lot harder. What is an easier string to pick?
One easier.
Yeah, not that one.
Take away the parentheses, maybe?
Yeah, so that's almost better. So like this, we have 1 0 with a lot of 1 0 with a lot of ones after it, 1 0 with a lot of ones. The issue here is that the first P characters are not the same. So we still have work to do. This will work, but it's a lot harder. What is something that we can make even easier than this? How can we enforce the first P characters to all be the same?
With the P with the 0.
Right. Yeah, that's what I'm going for. So what I'm going for is P on the zeros. A bunch of zeros at the front with a single 1, then a bunch of zeros with a single 1. Okay? So now we have exactly one case to deal with, which is nice. So we know, what do we know about the X part, the Y part, and the Z part as a result of this? Because we made this string easier. Well, what can the X part contain? Because the first P characters are all zeros. It can only have zeros. We don't know exactly how many, but let's just say alpha again to keep with the theme. Let's just say that Y has beta zeros again, where beta is at least 1 to remind ourselves. And the Z part must have all the other characters. So P minus alpha minus beta, 1, 0 to the P, 1. Because that's just the rest of the string. Okay? You guys still awake? It's hard, I know. It's harder teaching it. All right, let's see. So it'll turn out any value of I other than 1 will work here too. So pick a value of I. That's not 1. 3. Okay, so 3 will work just fine. So let's pick I equal 3. So what does that look like? So we need to have 3 copies of Y for that reason. So X, Y, 3 copies is, we have alpha zeros for the X part. I'm going to put 3 beta zeros in for the Y cubed part, and then the Z part afterward. Yeah, go ahead.
How can you know if Y is going to work?
What's that?
So you said
Yeah, how do you know?
it's gonna work.
Yeah, how do you know? Experience. There are actually some languages where only a single value of I works at all. Here, infinitely many. The reason why this will work is that what's going to happen is that the middle of the string is going to be imbalanced. So the start of the strings on both halves will not match. We'll get to that. So it's just I know that because I'm putting zeros at the front or removing them, I'm going to imbalance where the split of the string is, the middle, so that one string has to start with one character and the other half must start with a different one. So that because they start with different characters, then therefore it can't be WW.
So should we also consider I equal to the 1 all the time?
Not always. So I can even show you an example where you must pick I equals 0, no other value works. But it's just that the vast majority of the time you'll pick like I equals 2. Yeah. So like small values of I usually work. Yeah.
Is that like the tricky part of these proofs, is picking the value?
Yeah, that's kind of what makes them a little difficult. The thing is that pretty much in this class you're going to pick I equals 2 or 0 pretty much for every time. So yeah, just stick with one of those. There are some proofs that like if you consider the language of zeros that have prime length, so a prime number of zeros, you can't actually pick a specific number for I. It'll actually depend on the decomposition. So that's a crazy proof. But most of the time you'll pick 0 or 2. Okay, so let's try to finish this before we fall asleep. So how many zeros on the front are left? What was it? So we had the P left over, so that never got deleted. How many betas left? Yeah, 2 beta, and the alphas got killed. So yeah, and then we have the 1, 0 to P1. Okay, well, let's see. So beta is at least 1, right? Because that's our one of the conditions. So beta is at least 1. So therefore, there are more zeros at the beginning than the end. Therefore, it's not of the form WW, right? You can tell by my tone it isn't. Why is that not good reasoning? Because I need to analyze what is the first half of the string, what is the second half. Well, no matter what happens, because we picked I equal 3, the number of zeros at the front is even. So the length of the string as a whole will always be even. So we can't say, oh, it's an odd length, therefore it's not of the form WW. What do we need to say? Well, what does the first half of the string look like? Where was the first half before we added zeros in? Where did the split fall on? Right. So originally, we had a bunch of zeros with a 1, and that's where the split is. A bunch of zeros with a 1. Where did the split happen? What happened to the split? Because we put characters in. It shifted. So now we have this kind of split. So we have some number of zeros with the split here, maybe more zeros after that, but then the 1 appears after, and then zeros and 1. So the split moves left, okay? But now, can you see why this can't be of the form WW? The same string twice, yeah.
Why did it move left?
It moved left because we added characters at the front. So the middle of the string must move left because we put more characters on the front. It's to split it in half, yeah.
When you say you add more characters, are you saying is that from the 2 beta?
Yeah, the 2 beta. We're inserting more zeros in. Well, can this be of the form some string and then the same string later? No, why not? What do you mean by the 1s?
One half has 1 0 with it.
Right. So first half equals all zeros. Second half has 1s. Therefore, it is not in L2 because it's not the same string twice. And so L2 is not regular. Another way you can say this is they don't end the same character. So that's another way you can say it. Cool. I'll see you tomorrow.